Hi, my name is Nick Borson, and this is the 8th in a series of videos about learning to program using PowerShell. The videos in this series are aimed at new programmers or non-programmers who want to learn how to code, and we're using PowerShell as our first programming language, and they kind of build on each other. So if you haven't already, you might want to go back and start at the beginning. I'll include a link to the playlist in the description. In this video, I'm going to talk about floating point numbers, which are numbers used in a computer to represent real numbers, numbers that can have fractional values. And this is kind of building on the previous video I did about binary numbers. So let's go ahead and take a look at floating point numbers. Okay, so let's start using some floating point numbers here, and I'll start by just assigning a number to a variable. I'll call it A, and I'll assign it 0.1. So 0.1 is not an integer, so A is not going to have an integer type. Sometimes we've assigned numbers to a variable and we saw that its type was int32. But let's see what the type of this is. A get type dot name, and it says it's a double. So double just means double precision floating point. There's also a float type. So if we say float A, then it's also going to be 0.1, and it's just the only difference is that a float type is 32 bits, and a double type is 64 bits, or 8 bytes. So the way that floating point numbers work, whether it's a float or a double, is that they store two different fields within the number, each of which has some number of bits, obviously more bits for a double than for a float, and those fields represent the significant digits, or the significand, and the exponent. So it's a bit like scientific notation. So for example, if we have some number, 1 million, say, we could just write it out by writing it all the zeros, or we can write it out, if we want to use, we can say something like 1e6, which is also a million. This is sort of a shorthand in PowerShell and some other languages for writing scientific notation. It means 1 times 10 to the 6th. Or we can say 1.2 e6. And we can take this number and we can use the number specifiers like we've used before, or the format specifiers, and we can say I want to use scientific notation, and I'm going to format this string. This is the format string, and this is a placeholder in the format string, and the 0 refers to the first argument index 0, which I'll just say 1.2 million. And the :e means I'm going to use the number format exponent. Okay, and it's going to give us, it's going to represent this number as in scientific notation. Okay, so that's one way. So this is just to illustrate the idea that that you can write a number using scientific notation. But the way it's actually represented inside the computer is essentially that. What's nice about scientific notation is we can write a number like 1.2 to the 100th times 10 to the 100th, or 10 to the 100th, which is quite a large number. And to write that down using actual digits, we'd have to write out 1, 2, and then 99 zeros. We might not have enough space. Certainly, we don't have enough space in our 32-bit or 64-bit variable to hold, or object to hold, a number with 99 decimal places. So using this kind of form where we actually store an exponent along with some number of significant digits is how we do that. And then if we have a negative exponent, let's just say -5, then okay, that's a double. And if I want to format that without scientific notation, if I say 0n, well, that's interesting. I think I need more decimal places. Let's give it 10 decimal places. Okay, then we see that this is actually, we take the decimal place is 1.2, right? We start with 1.2 when we created this number, and then we take the decimal place and move it 5 places to the left because it's times 10 to the negative 5, and this is the value that represents, 0.000012. So in a floating point number, that's essentially what we're doing. So if you want to read more about it, Wikipedia has lots of information. You take a number that's like 1.2345. The significant digits of that are the significand, and then there's an exponent that's also stored. And so the actual 32-bit or 64-bit single or double precision floating point number contains these two fields as separate fields, and then it knows how to do calculations based on that. So, so one thing about that kind of notation, though, is it does mean that the numbers are not necessarily stored precisely, right? So if you have a very large number, then, if you have a 1 followed by 100 zeros and then another 1 at the end, then you're only storing the first few significant digits. Quite a few digits maybe, but only the first few significant digits. So that 1 at the end, you're going to lose. That's just going to be not retained in the variable. So you can't always represent every number precisely. You can represent very large numbers. You can represent very tiny fractions. You can represent very large negative numbers, but you can't always represent every number precisely. So let's take an example of that. I'm just going to assign, I'm going to let a equal 0.1. Now you would think this wouldn't be any problem. I'll let b equal 0.1. And if we say, is a equal to b, so this is a Boolean expression, right? Because we're using the Boolean equals operator, then as you would expect, a and b are equal. But what if we do some calculations on b? Let's say we want to do something 10 times. So one easy way of doing it, I'm going to just have a range from 0 to 10. I'm going to pipe that to the for each object, and then I'll say b multiply b by 0.1. So I'm going to multiply b by 0.1 10 times. Okay, b is now a pretty small number. And then if I multiply b by 10 times. Okay, so I've multiplied b by 0.1, which is 1/10, 10 times, and then multiplied it by 10 times. We should end up back up with the number we started with. And if I just type b, so it appears. But now what if I type is a equal to b? Well, that's interesting. They're not actually equal. And the reason for that is the loss of precision I was talking about. A is close to 1/10 and b is also close to 1/10, but neither of them is exactly 1/10. To see that, we can again use the string formatting operation. So let's look at a, and we'll give it a number format, and we're going to give it 20 decimal digits of precision. So we'll use the format. Okay, so this is a formatted with 20 digits of precision, and we see that way out here shows the right side of the number. There's quite a few decimal places where it's just 0.100000. So to quite a high degree of precision, it is actually just 0.1. But there is some error in there if we go way down, quite a few digits down. If we do the same thing with b, we see that slightly farther off. All those calculations where we divided by 10 and multiplied by 10, some error crept in. So b is not exactly the same as a. You would think, maybe, why is this happening for 0.1, for 1/10 or something like that? Seems like it should be easy to represent exactly. But actually in binary, 1/10 cannot be represented exactly. And the reason is that for kind of the same reason that you can't represent something like 1/3 in decimal. So in decimal, we know that 1/3 is equal to 0.333333, and you have to go on indefinitely. You're never going to get the exact value of 1/3. To get, if we say, for example, just 0.3, that's really equivalent to 3/10, right? which is not exactly equal to 1/3 because 3 doesn't divide evenly into 10. If we say 0.33, we're going to get a closer approximation, 33 over 100. But again, it's not going to be exactly 1/3 because 3 doesn't divide evenly into 100. The closest we can get is 33, but we still have a remainder of 1. And likewise, if we just keep adding more digits, 333 over 1,000, well, divide 3 into 1,000, it's still not going to divide evenly. We're just going to get 333, but we'll still have a remainder of 1. So that's still the closest we can get with 1,000 as the denominator. And the point is that no matter how many digits, no matter how many digits we have in the decimal form, the denominator is always going to be some power of 10. And 3 is not going to divide evenly into any power of 10 because the factors, because if we factor 10, the prime factors of 10 are 2 and 5. Neither of those is a 3. So no matter how many times you multiply 10 by itself, it's not going to have 3 as a factor. Well, when you're using binary numbers, and including floating point numbers in this, because floating point numbers are still using binary, they're just using binary fractions essentially, then the denominator is always going to be some power of 2. And no power of 2 is ever going to have 5 as a factor. So you're not ever going to be able to divide 10 evenly into a power of 2. So you can get very close to 1/10, but you can't actually get 1/10. Okay, so floating point numbers are ways of representing very large numbers because you have these exponents and very small fractions, and but they don't represent. There are some numbers that they do not represent precisely, and which is really no different than when we're working with decimal fractions and decimal exponents. You know, if you want to write pi in decimal, you're never going to get exactly pi. If you want to write 1/3 in decimal, you're never going to get exactly 1/3 for somewhat different reasons. Okay, so last thing I'd like to share is that there are some constants that you can refer to in the .NET runtime, which is PowerShell is built on. So each of the numeric types has some constants defined to refer to the maximum and minimum and some other values. So, for example, for int 32, we can say int 32. We can get the max value, and that's going to give us this number, which is 2 to the 31 minus 1, as it happens, for the reasons I described in the previous video. If I say int 32 min value, that's going to be negative 2 to the 31, but it's certainly much more readable to say, if you're concerned about whether something is can be represented within the range of an int 32, then using these named constants is certainly a nice way to do it. And int 16 and int 16 has min value and max value. And for an 8-bit type, also each of those has unsigned equivalents. So there's uint 32 max value. So an unsigned 32-bit integer can be larger than a signed 32-bit integer because we don't have half the space reserved for negative numbers. So the higher bit, the highest bit can be set to 1 for unsigned, but the min value is simply 0. And finally, for as far as integers go, the 8-bit types are called byte for an unsigned 8-bit type, and sbyte for a signed 8-bit type. So in terms of floating point, we have double. By the way, this notation we're using here is the type name enclosed in square brackets. So a lot of types have what are called static methods you don't call on a specific object, but just call on the type itself. And then when we use the colon then to refer to these static methods. So double has a max value, which is very large, 1.79 something times 10 to the 308th. And float has a max value, which is also large, but not as large, because it has fewer bits to work with. It has a much smaller exponent and also fewer significant digits. Okay, so that's floating point numbers. You can represent a lot of you can represent fractional numbers. They're sort of an approximation of the mathematical concept of a real number. And the way that they work is to store is essentially like scientific notation. They store some significant digits, and then they store an exponent. And that means that if you're storing some fractions or extremely large numbers that you may not have the exact value, you can lose some precision, but they are still a very useful and effective way of representing real numbers. All right, thanks for watching, and I'll talk to you next time.